students, greetings of the day. This is our second session with the chapter Gravitation. In first session, I had simply introduced gravitation, gravitational forces, and in this session, I am going to start gravitational field intensity. So let us learn about the gravitational field intensity in detail. Let us get started. In last session, we had discussed about gravitational force between two particle masses. Now I am going to consider the continuous mass distribution. If it is not a particle mass but an extended bodies, how will be the force calculated? So let us consider this. Let this be an extended body and we have to write force exerted by this body which is having mass capital M on the small particle which is having mass small m. So how this will be calculated? Now again, as we calculate all the parameters using first an elemental particle and then integrate it over the body, the same method has to be applied here. So first we will consider a very small mass which can be taken as an elemental mass and then write force between these two masses and integrate it over the whole body. But do remember, while calculating force, since it is a vector, so directly integration will not be possible because the forces will be in different directions. So we have to write Fx and then Fy and then Fz and then we can write finally F to be equal to Fxi plus Fyj plus Fzk. So if the extended body is such that the forces will be in different directions, always we have to write the forces in component form and then integrate it over the entire body. Here I have taken one example. A point mass m and a thin uniform rod which is having mass capital M and length L are shown in figure. Find out the force of attraction between them. So we have to calculate force on the small particle mass due to this extended rod. As we know that mutual interaction is equal and opposite for both the bodies, so always it will be easier to calculate force on the particle mass. So let us do it here. First I am considering a small elemental particle mass which is having mass dm. If this be at a distance x from the small mass and its width is equal to dx, what will be the force then? dF can be written as g m dm upon x square. But we are interested in the force exerted by the whole rod, so it should be integrated over the entire length of rod. F we can write as integration of dF, that will be equal to gm can be taken outside the integral. Inside it will be, now dm can be written as mass of this elemental particle, that will be equal to mass per unit length into length of that particle, that is dx. So it is m by L into dx upon x square. Now what is the variation in x? X has to be from a, as this distance is given a, to a plus L. So lower limit is a and the upper a plus L. Now if I integrate it, this will give gm m upon L. Now this is integration of x to the power minus 2 dx. So it has to be with one minus sign 1 by x within limits a to a plus L. Now on substituting limit, it will be gmm upon L 1 by, since minus sign I have taken inside, so first I have to write the lower limit and then the upper limit, which is L plus A. That will give L multiplied with A plus L, and in numerator it has to be G M M L. These two L got cancelled and the final answer we got as GMM upon A into A plus L. This is the force of interaction between the particle mass and the rod. With this, now you can calculate force between two extended bodies. Now let us see what is the definition of mass. See, depending on the situation, mass can be defined in two categories. It can be either inertial mass or the gravitational mass. So first let us see what is inertial and what is a gravitational mass. Now as we know that mass of a body is the quantity of matter which is possessed by the body. So how it can be categorized based on two different concepts. First is the inertial mass. Now inertial mass of a body, we can relate it to inertia of linear motion. While discussing laws of motion also I had said for the first law of motion, this is the definition of mass, which actually is measurement of inertia of linear motion. So as defined by second law, we can write F to be equal to ma. Here this mass has to be the inertial mass, and from this we can write mi to be equal to F upon a. This mi of the body in the case is known as inertial mass. If we write a to be equal to 1, then mi becomes equal to F. So we can define inertial mass as it is equal to the magnitude of external force required to produce unit acceleration in the body. In fact, inertial mass of a body is the measurement of ability of the body to oppose the production of acceleration in its motion by an external force. So this is how inertial mass can be defined mathematically. Now let us see what are the properties of inertial mass. So many properties can be discussed for inertial mass. The first thing is that inertial mass of a body is proportional to the quantity of matter. So it is proportional to quantity of matter in the body. The second property can be written as inertial mass is independent of size, shape and state of body. It does not depend on what is the shape, what is the size, it only depends on the quantity of matter inside the body. So it is independent of size, shape and state of body. The third property can be written as inertial mass of a body does not depend on temperature. So it is independent of temperature as well. When temperature changes, of course its length will change, its volume will change, area may change, even density will change, but mass will not change with change in temperature. The fourth one we can consider as that inertial mass is not affected by presence or absence of any other body. So it is unaffected by the surrounding, we can say. The next property can be considered as inertial mass is conserved. Whenever two bodies combine physically or chemically, this has to be conserved. So conservation law has to be valid. Now do remember that here we are considering the classical mechanics where mass has to be conserved. Though we know that in quantum mechanics it is not conserved, mass can be converted into energy and vice versa. But according to Newtonian mechanics, because inertial mass is defined by Newton's law itself, so we can consider that mass has to be conserved. One more property we can say that inertial mass can be added by simple laws of algebra irrespective of the material of the bodies. So since it is a scalar, this can be verified as well. These are the properties of inertial mass. Now we know that inertial mass of a body increases with speed of body. So if we go beyond the Newtonian mechanics, we can define variation of mass with speed of body as well. But here we are considering only classical mechanics, so it can be excluded. Now let us come to the other category of mass, that is known as gravitational mass. Now what is gravitational mass? Gravitational mass of a body is related to gravitational pull on the body, and it is defined by Newton's law of gravitation. So if a body has mass mg which is placed on the surface of earth which has radius r and mass m, then gravitational pull on the body can be written as F we can write as 𝕃𝑚𝑔 upon r square. Here this term mg is gravitational mass of the body, which has come from the concept of gravitational pull of earth. So this mg can be written as Fr square upon g multiplied with mass of earth. So this term, it can be written as F upon I, where I is a constant which is gm upon r square, because these are all constant at the surface of earth. So I have simply replaced the whole term with I. Now we can define gravitational mass as force, gravitational pull exerted by the earth on the body upon some constant. If we substitute this value to be 1, then directly mg can be written as equal to the gravitational pull. So numerically, this mass will be equal to the force experienced by the body when gravitational field is of unit intensity. Later I am going to explain this also, how gm upon r square can be written as gravitational field intensity. Now we can see what is the equivalence among these two masses, inertial and gravitational masses. The first equivalence we can consider as that both are measured in same unit. So unit has to be same for both the masses. The second thing is that both are scalar. Gravitational as well as inertial mass is a scalar quantity. The third one is that they do not depend on shape and state of body. They both are independent of state and shape and size. So these are the points which can prove equivalence of masses. But what is dissimilar between two masses? So dissimilarities also we can discuss. The first dissimilarity is that the gravitational mass of a body is affected by presence of other bodies near it, whereas we had seen that inertial mass is unaffected by the surrounding, because we know that if other bodies are present in vicinity of a given body, then of course they also will apply some gravitational pull. So we cannot say that gravitational mass is independent of the surrounding. It does depend on surrounding as well. One more dissimilarity we can quote here, that inertial mass of a body is measured by finding its acceleration produced by applied force, and gravity plays no part in the measurement. Whereas for gravitational mass, it is measured by finding gravitational pull on it, so inertia plays a part in this. And this is the reason why gravitational mass is measured by spring balance, whereas inertial mass is measured by inertial balance. Otherwise, numerically on the surface of earth, they both are equivalent. They are equal to each other numerically. Now let us check for their numerical values. Let us consider two bodies A and B of gravitational masses. For A, I am writing the gravitational mass as mg, and for B, this is mg dash. Now let us consider that these are placed at equal distance r from a third body. Let that body be earth. So if m be the gravitational mass of body C, that is the third mass that we have considered to be earth, then from Newton's law of gravitation we can write gravitational force exerted by earth on A can be written as F will be equal to gm mg upon r square. Similarly, gravitational force exerted by earth on B can be written as, let us denote that by F dash, so it will be gm m dashed upon r square. If we take the ratio F by F dashed, we will get the value to be equal to mg upon mg dash. Similarly, if we consider mi and mi dashed be the inertial masses of bodies A and B. So now their inertial masses are mi and mi dashed. Then if we consider that both bodies are allowed to fall in vacuum from the same place under the action of gravity, where acceleration due to gravity can be written as small g, then we can write F to be equal to mig and F dash to be equal to mi dashed g. So if we take ratio here, this F upon F dashed will come out to be mi upon mi dashed. From here we can see equivalence of these ratio of these two masses. So we got finally mg upon mg dashed to be equal to mi upon mi dashed, which proves equivalence of the masses, gravitational mass and the inertial mass. Actually, this idea of equivalence of inertial mass and gravitational mass of a body led Einstein to predict the general theory of relativity, which is the modern theory of gravitation. But it is beyond the scope of our syllabus, so let us stick to the things that is in our syllabus, and the next thing to be discussed is intensity of gravitational field. What is intensity of gravitational field? Intensity of gravitational field can be defined as the force experienced by a body of unit mass placed at any point, provided the presence of unit mass does not disturb the original gravitational field. Then field at that point will be equal to the force experienced by the body. It should be always directed towards the center of gravity of the body whose gravitational field is considered. Intensity of gravitational field at a point, of course, has to be a vector quantity, as this is defined by the force and generally it is denoted by E. So E we can define mathematically as force experienced by the unit mass. This is how intensity of gravitational field can be defined. Of course, it is the characteristic of a point in space if we are interested in getting field at a certain point. Even if there is no mass to experience that field, the field will be there at the considered point. So field is not the characteristic of a body which is experiencing the field, it is characteristic of the point at which we are calculating the field. Now how to calculate its value? Let us consider that m be the mass of a body, and if it is an extended body, then it has some center of gravity which can be considered at its geometrical center. Now if F is the gravitational force of attraction experienced by another test mass, which is written here as m0, which is the test mass, and it is placed at some point P in the gravitational field of the body such that O we are considering the center of mass of the body m, and the other one is test mass which is m0. Distance between these two are equal to x. So we can define that force on mass m0 has to be equal to gm0 upon x square, and then intensity can be written as gm upon x square. Now since it is a vector quantity, so we have to define its direction as well. What will be the direction? As we know that gravitational force has to be towards the point O, so E can be written vectorially as this is minus gmx square and then unit vector along x, where x is position vector of m0. So if we write in vector form x, then it will be towards m0. Here the intensity will be in the direction that is towards the mass which is producing the field. And you can see that when x increases, value of E will decrease, and when x is infinity, then only its value will be 0. It does mean that intensity of gravitational field is 0 only at infinite distances, but practically for very large distances, of course, we can consider value of field to be equal to 0. What should be its dimension? Since it is force per unit mass, so its dimension should be equal to, for force we can write mLt minus 2 upon mass. As we can see here that this is an acceleration term. So gravitational field intensity is actually an acceleration term, and this is the reason why we call gravitational field of Earth to be equal to acceleration due to gravity, because we are getting an acceleration term, so it is written as acceleration due to gravity. Now let us solve few questions based on this concept. The first question is, find relation between the gravitational field on the surface of two planets A and B of masses ma, mb and radii Ra and Rb respectively, if first we have to consider they are having equal mass. Okay, so let us start with this. Intensity of field can be written as, for A, this value will be equal to Gma upon Ra square. Now if we substitute the value of Ma, then it can be written as G 4 by 3 pi r cube, because we are writing masses of the planets, it has to be spherical. So this will be 4 by 3 pi Ra cube multiplied with density of A upon Ra square. That will be equal to 4 by 3 G pi rho A Ra, where rho A is density of planet A. Similarly, we can write Eb to be equal to the similar result we will get. So directly it can be written as 4 by 3 G pi rho B Rb. For our first case, we have to consider Ma to be equal to Mb. So directly we can take ratio of Ea upon Eb, that will be equal to, as masses are equal, so it has to be Rb square upon Ra square. And for the second one, as we have derived here in terms of density, and since densities are equal, so we can write Ea upon Eb to be equal to Ra upon Rb. As you can see that E is proportional to R if density is taken constant. So we got these two results. If they have equal mass, intensity ratio has to be equal to square of inverse of radii, and if they have same density, intensity ratio has to be equal to that of ratio of their radii. One more question I have. Two masses 90 kg and 160 kg are at a distance 5 meter apart. Compute the magnitude of intensity of gravitational field at a point which is at a distance 3 meter from 90 kg and 4 meter from the 160 kg mass. Let us first draw the situation. This is point A, here is point B. The masses are given 90 kg and 160 kg. Distance between this is 5 meter. If we consider another point C here, which is at a distance 3 meter from A, this distance is 3 meter and this one is 4 meter. Of course, as the side length suggests, this angle has to be equal to 90 degree. Now we have to calculate magnitude of intensity at the point C. So let us consider magnitude of intensity at point C due to A first. So it has to be equal to E due to A. If I am writing, what should be its direction? It has to be along CA. Its magnitude will be equal to Gm upon R square. So this is G into 90 upon the distance given is 3. So 9 here. What about the intensity due to B? It has to be equal to G. This time mass is 160. So 160 upon square of 4, which is 16. And what is its direction? It has to be along BC. So now we can write the resultant E has to be equal to, as EA and EB are perpendicular to each other. So we can write G can be taken common. Then this value will be equal to, this was 10G and this also 10G. So we have to write square root of 100 plus 100, that is equal to 10 root 2G. If I substitute value of g here, this will come out to be 10 root 2 into 6.67 into 10 to the power minus 11. That is equal to 9.43 into 10 to the power minus 10 Newton per kg. So this is the resultant intensity at C due to the masses A and B. With this, now today's session is complete. We discussed about gravitational field intensity today and then few questions based on field intensity. In the next session, I am going to discuss about how field intensity due to gravity changes with height or with depth or with shape of earth or with rotation of earth. So it is variation in G due to different parameters. So let us look forward for the next session. Bye.